So here we're asked to find the integral around a closed curve C, and C is given as a circle of radius 3. So really there's nothing that prevents me from approaching this from the standpoint of saying we want to parametrize our particular circle, and then using those in the integral above to evaluate it. But if we look at that, what we would see is that there's lots of places where we have to sub in, including the differentials, what the parametrization is for this particular curve. And it's already a somewhat complicated looking function, which means that we're likely going to end up with something even much more complicated to anti-differentiate. So in this case, because C is a closed curve and we have a particular defined region D, I can actually integrate using Green's theorem here over the region D contained within that circle instead of integrating around the positively oriented curve here. So let's apply it that way, and I think we'll find out that that turns out to be a much nicer way to do this integral. So we'll remember that Green's theorem is the integral over the curve C, positively oriented and closed, of p dx plus q dy, and that is equal to the double integral over the region D of q sub x minus p sub y dA, where p and q here are these functions represented in our integrand. So now I need the partial of q with respect to x, which is 7, and the partial of p with respect to y, which is 3. So our integrand just reduces down to 4. This is the double integral over the region D of 4 dA. Now, although our particular region D here happens to be circular and we'll want to compute our double integral down here using polar coordinates, we want to make sure that we pay attention to how we applied Green's theorem in a situation like this. And that was that we applied Green's theorem as it sits directly, and then we're going to do the integral using our polar coordinates. And I think it's important to do that. Green's theorem is all set up to have lots of stuff involving rectangular coordinates. So we want to make sure we maintain that relationship in its rightful form, as opposed to trying to convert too early to a different system of measurement. So now that we've got our integral set up using Green's theorem, at this point it's pretty trivial. We know that the integral in polar coordinates is going to set up with limits that go from 0 less than or equal to r less than or equal to 3, and theta is going to go from 0 to 2 pi to get us all the way around. Again, we want to make sure we remember in polar coordinates dA is r dr d theta, and now it's just a matter of setting it up. So we get our double integral of 4r dr d theta. R is going to go from 0 to 3, and theta goes from 0 to 2 pi. And I've actually worked this out. It's a very simple integral, but I've worked this out. It's 36 pi, just so we have an answer here. So this, again, is really just showing you the power of Green's theorem on these closed and bounded regions. We want to make sure that when we have the opportunity to do that, as long as this region D over here is simple, then we can easily compute that double integral. And in this case, again, it illustrates, it just reduces down to something extremely simple for us to process.